At this point, we know anytime we have a charge configuration, it holds some amount of potential energy, either positive or negative. A charged capacitor technically makes up a charged configuration too, doesn't it? That means there's some potential energy associated with a charged capacitor, either positive or negative energy. Let's try to reason which we would expect it to be. We know if we have like charges together, the potential energy of the configuration is positive, and it's larger if the charges are closer together, and smaller if the charges are farther apart, because the energy is inversely proportional to R. If we have a pair of opposite charges, though, we have negative potential energy. It's a lower energy state than if the charges were infinitely far away, at which point the electric potential energy would be zero. The electric potential energy decreases as we move them closer together, and it increases as we move them farther apart in this case. So, do we expect a capacitor to have an electric potential energy greater than zero or less than zero? If we look at just one plate specifically, what we see in a capacitor is that the positive charges on the positive plate are very close together. I'll actually move the plate out of the way so we can see the charges more clearly, but imagine the plate's still there. In fact, I've also wildly exaggerated the size of the charges here. In reality, they're super small and super close together by virtue of being so small, and they're also much more dense than we have here. The same can be said for the negative plate. The negative charges are very small and very close together on the whole. We recall that like charges bunched together contribute to positive potential energy because the Q values have the same sign in the basic definition. And opposite charges contribute to negative potential energy. But we saw that the distance also matters. The smaller the distance between the charges, the more dramatic the effect because we have KQQ divided by R. Once again, we'll take away the plate for the sake of clarity, but suppose it's still there. From this view, we see that the positive charges are very close to each other and the negative charges are just as close. But what about between the two plates? Taking a look at this situation from our original vantage point, we see that comparatively speaking, the distance between the plates is actually quite large. This distance, if we call it d, it's much larger than the distance between the positive charges among each other, or the distance between the negative charges among each other. So we have a large positive potential energy from the positive charges being close together, a large positive potential energy from the negative charges being close together, and a small negative potential energy from the positive charges being far away from the negative charges. This suggests for us that the energy state of a capacitor is positive. It takes energy to bring these positive charges bunched up really close together, and same with the negative charges, even if the positive charges themselves are attracted to the distant negative charges far away on the other plate. That was kind of a hand-wavy argument, so if none of that is convincing, it doesn't matter, because now we're actually about to find out how to quantify the exact potential energy on a capacitor. How? If you remember when we were talking about electric potential energy, the more charges we had to deal with, the more terms we had to deal with quadratically. Even dealing with only 5 charges was almost totally intractable. So how do we expect to deal with this massive amount of charges we have here? And actually, the amount you see here still unfathomably underestimates the actual amount of charges on each plate. So how are we going to deal with this? The answer is calculus. One of the great things about calculus is it sometimes gives us the ability to turn hard series problems into easy integration problems. Now, what we're about to do is set up just one way a capacitor can be charged up, but this isn't how a capacitor actually charges up. What we only care about is the final energy state, so using any method of transferring charge over would result in the same final energy state on the capacitor. Imagine we have some capacitor not connected to a battery or anything, and it's already partially charged to some value little q on each side. Remember, the whole capacitor has a net charge of 0, but when we say charge on a capacitor, we really just mean the magnitude of the charge on one of the plates. And we just take some small positive amount of charge dq and physically move it from the negative plate to the other. The negative plate becomes more negative by conservation of charge, and the positive plate becomes more positive, of course, so we're increasing the charge difference between the plates. How much work does it take for us to move this dq over to the other plate? Let's take it one step at a time. First of all, why does it require any work from us at all? This positive dq is attracted to the negative plate and repelled by the positive plate, so we're ripping it apart from its friends at the negative plate and taking it over to where it doesn't want to be, close to all these positive charges. More technically, the plates generate an electric field pointing to the right. So in moving a small positive charge against that electric field, it requires positive work on our part. What is the work done by the electric field when we move this dq to the other side? The negative of the work done by the electric field will give us the work required by us, since the electric force points opposite to the force that we apply on the dq. We do positive work, while the electric field does negative work. Also, we remember we can write the work done by the electric field as the electric force dotted with the displacement, provided the electric force is constant, which it is here since the electric field is constant. And we remember we can write negative E dot S as the potential difference that the charge moved through, so negative delta V is just E dot S. Alternatively, the work done by the electric field corresponds to the negative change in electric potential energy. We'll call it du here, since the change is infinitesimal, provided dq is infinitesimal. Then the tiny change in electric potential energy of the system is equal to dq times the potential difference, delta V. In that case, all we have to do if we want the total potential energy of the capacitor, we just have to integrate each tiny change in electric potential energy, and that involves integrating the charge dq from q equals 0 all the way to q equals capital Q, which we'll call the total charge of the capacitor. Now we know what dq is, it's the charge we've just moved from one plate to the other plate, but what's delta V here? Delta V is the potential difference between the two plates, and we remember that we can write the capacitance of the capacitor as whatever little q happens to be right then, divided by whatever delta V is at that time. So delta V is equal to little q over c for q at any point during the integration. This expression kind of makes sense. You can imagine when little q is 0, it takes effectively no work to move dq from one plate to the other plate, because it doesn't have to bridge any charge difference. But as little q gets bigger and bigger, the plate becomes more and more charged up, and doesn't want to accept new positive charge, which will repel all the other positive charge that's already on the plate. So it takes more and more energy to push incremental charge onto the other plate. But coming back to the expression here, what we've done is actually really slick. We know the capacitance is just a constant which depends on the geometry of the capacitors, so we can pull 1 over c out of the integral, and we're left with this super clean integral here. What we end up with then is that the electric potential energy of a charged capacitor is capital Q squared over 2c, where capital Q is the final charge of the capacitor. If we want to express this in terms of delta V, we can do that too using our simple capacitance formula. I encourage you to work out the details if you're interested. The most common formula I usually see is the 1/2 CV squared formula. The potential energy of a capacitor is half the capacitance times delta V squared. And we finally landed on an important set of formulas for the electrical energy inside a capacitor. Now, moving on to something else, it's pretty common to consider the energy of a capacitor as stored in the electric field between the two conductors. After all, it'd be kind of odd to think of the energy as stored in the charges themselves. They're just the same charges they were when they were really far away. Instead, we might say the energy is stored in the electric field. So how might we relate the potential energy of a capacitor to the electric field? Maybe there is some relationship we can uncover between the two. Well, we remember that for a uniform electric field, we can write the potential difference as just negative E dot S, where S is the position vector between the two respective points we care about, and E is the electric field. Then if we only care about the magnitude of the potential difference between the capacitor's plates like we do here, we can write it as E times d, where d is the distance between the plates and E is the magnitude of the electric field between the plates. Also, we remember we can write the capacitance of a parallel plate capacitor as epsilon naught A over d, where A is the area of one of the plates. Some stuff cancels, and what we're left with is this interesting formula here. Now, crucially, the volume between the two parallel plates is given by A times d, where A is the area of one of the plates and d is the distance between the plates. We can see that here, right? The volume just makes up this rectangular box, and the volume of the box is the area of the big face A times its depth d. This is the volume of space between the two plates. Then the electric potential energy per unit volume inside a parallel plate capacitor is given by this useful formula here. It's just 1/2 epsilon naught times the magnitude of the electric field squared. We also call this the electric potential energy density, or little u sub e. Some other names for it are electric field energy density of the electric field, electrical energy density, and so on. But, so what? What's the point of even deriving this formula here? Well, we can't prove it now because it's beyond the scope of just intro physics, but this formula doesn't only hold inside a parallel plate capacitor, it holds everywhere in space. Anywhere there's an electric field, the electric potential energy density in some small region only depends on the electric field in that region. It's a bit of an abstract concept, but luckily it's not the most difficult concept to implement since the formula is pretty simple. If you ever take a higher level physics class, you'll explore this in much more detail. This is just the beginning for you. And if you're not planning on taking a higher level physics class, well...
Don't worry about it. Don't worry about it, sweetheart. Don't worry about it, sweetheart. Don't worry about it. It's the split